name is Daniel Ortega. I'm a student in industrial engineering, and today I'm going to explain to you the TV diagram. TV diagram has nothing to do with television. Actually, it's a very simple but really important topic into thermodynamics, which is really crucial to understanding if we're going forward in the class. T here stands for temperature, V stands for volume, and diagram, well, it's because it's a graphic way to understand what we're going to see. So it starts as a graphic like this. T is on the y-axis, temperature. On the x-axis, we have volume. Now, what this is used for, it's used to understand the processes of the different substances in thermodynamics. It is really used to show from step A, from the initial step, to the final step, how the temperature and how the volume changes in between. We're going to start first with water as the example. So there's a common misconception actually in thermodynamics of normal people. They think that water, it evaporates at 100 degrees. So yes, at 100 degrees it evaporates, but it doesn't just transform itself into vapor out of nowhere. If we think about the kitchen, when we make water boil, when it hits 100 degrees, the bubbles start to rise, but it doesn't just disappear into vapor. Instead, what happens is, for example, let's take water at 1 atmosphere, and the pressure is important because 100 degrees Celsius is only valid for 1 atmosphere of pressure. It starts at a low temperature and low volume relatively. Then it starts to go up as we want to boil it. But careful, it doesn't just go linearly. It starts to make a curve towards the 100 degrees in temperature. Not asymptotically, because at some point it is going to touch 100 degrees. Now this is what's called the saturated liquid phase. Before it is undercooled, when it touches this, it stays in a plateau. So the temperature is not going to rise in between this point and the saturated vapor point. This is called the saturation level, or the evaporation level of 100 degrees as we know here. And this is called the saturated vapor point. What happens in between these two phases is that the liquid gradually becomes a vapor. We can see here, as let's say the liquid, it comprises of 100% of the water, and vapor is at 0. But as the temperature stays the same, but the volume increases, the liquid goes down in the process, and the volume goes up until it fills 100% of the water. Only after this can it go back up. Again, not linearly, the temperature rises again. This is only for one example of water, which is this set temperature and volume. But let's say another example of water with a higher temperature initially and the same volume. It would start around here in the TV diagram. And let's say we want to do the same thing with this sample of water. We want it to be boiling and to evaporate completely. So we're going to first raise its temperature, and it's going to go rise up, and it's going to converge again until it reaches a point where it's going to be the saturated liquid temperature. Depending on what the sample is, it's going to have a different temperature, and the pressure too is probably going to be different. Now, when it's in this, its temperature is going to plateau again, but it's not going to last as long, the plateau, in terms of volume. It's going to stop here for its saturated vapor point, and then it's going to go back up again. And if we do this with many samples, we're actually going to see a trend, which is that it forms a dome if we rely all the saturation points. And with this, we can easily predict the temperatures at which water is going to evaporate. Thank you very much for listening.